We know all bodies radiate at all temperature. As the temperature decreases, so what is the basic idea? See, try to understand the basic ideas involved. If there's a body is there, mass m, specific heat, temperature, it will start cooling. It will give out radiation. Then temperature decreases according to Wien's displacement law. If temperature decreases, so what do you expect the wavelength? Wavelength should increase. So that wavelength is what is telling here. Some. Okay, they may mix up ideas like this, which from radiation to this particular thing. So directly, since why temperature of body, why the wavelength of body, why the wavelength of radiation emitted by a body will increase means this is a basic thing. Cooling object it is. No, so very simple idea, that one. So instead of giving this, you may interlink the question with the help of this one. So we know how to calculate temperature at any time t by using Stephen's law. Okay, so this should be equal to minus ms dt by dt. Solving will get temperature as a function of time. So that function of time t is what I'm going to substitute here. Then I'll get the corresponding lambda. There's a background. Okay, now let's get into the our photoelectric effect problem. Okay, we have a metal sheet. And there's an incident wavelength, which is lambda equal to 3000 plus 40, that one. So that the power incident on the sheet is constant. Okay, he has given incident power, Pi will take it. With the metal plate is earthed. Find the maximum photoelectric current. So from here, what happened? A current will start flowing here. The photo emission efficiencies, and he has given HC also, and remains the photo electron efficiency remains constant is telling. One more condition he has put it. We have work function for this. When do that photo electron emission stops? I think there's a primary question is what we have to answer. Rest all everything we can manage. Once the wavelength, so like a energy of the photon, if it is equal to work function. So there's one threshold wavelength, no? When the wavelength becomes greater than threshold wavelength, no more photoelectron emission will be there. He's asking maximum photo current, and that to this wavelength is what varying with the time t. Okay, let's do one thing. Shall we go for directly the saturation current formula? Or come for this one. Number of photons incident will take like this. Because here we have efficiency. So again, the same old formulas. So what you learn at one place, the same thing you're going to apply. Number of photons incident. They should be equal to the power of a source by energy of photon, hc by lambda. So ps lambda by sc. This lambda is varying with the time. Okay, that is another thing. This lambda is not a constant, varying with the time. Then what is the efficiency now? Efficiency is telling 0.01%. Means for these many photons incident, how much will you get it? This one by 100, no?
To the power of 4, sir, by 10 to the power of
10 to the power of minus 4 should come. So number of Yeah. Photons, number of photo electrons emitted per second should be equal to, shall we write the efficiency? Efficiency is how much? This eta I'll call efficiency 0.01%, which is equal to, okay, that or if you want, you bring the theta, which is equal to PS lambda
Ni into eta, sir.
Ni by 10 power 4, sir.
Ni by 10 to power of 4.
Ni into eta, sir.
Ni into eta, number of electrons emitted, no? Okay, yeah, that one. Okay, this will come here. Okay, look at this. I got any. So what to do for this? Is asking maximum current. So definitely according to this equation, lambda is a function of time, no? I'll dump all, now I'll bring the substitution. Okay, look at now here. Look at the with time, what will happen to number of electrons that are ejected? Will keep on increase. Will keep on increase. So therefore, what should happen to the current? Current should also keep on increase. So here shall we put it like the electrons will be ejected? Is asking for the maximum photo electron current. Why current will come here? Why current should flow?
Potential difference will be developed.
Potential difference will be there. Say I have this plate ejects electron, this will acquire a positive charge. There's a ground. So therefore, and the positive charge will flow from the conductor to the earth. All electrons will come and flow here. So because of flow of charge across the wire, so this is the wire. There'll be a flow of current. So the current direction is what I should put in this one. I. Okay, that current, when it will be maximum is telling. So how to decide? So shall we say that with the time this keep on increase? And what is the expression for current? Current should be equal to rate of flow of charge. This is nothing but the number of electrons emitted per second. So shall we multiply this with charge of electron? I'll get a current. Simplest thing, because this is nothing but the charge. This will be, so into charge of electron, what do we get? We get expression for current. So let me go for, shall I divide or shall I multiply? Multiplying that one. Current should flow from I to lower potential. No? What all current is due to flow of conventional charge? Electrons will flow from the earth.
Using electrons, sir. Okay, sir, understood.
Okay, fine. Yeah, simple. Say this will acquire positive charge. So therefore, so what we should do, the positive charge will flow from conductor to the earth. It is like this. Huh? So what is E? E I think this E is emissivity. Huh? This is charge of electron. I think I'll write Q. Okay, this you are going to put it. Okay, let me bring this symbol also. Yeah, we have everything here now. So this is 3000. So look at this current. So shall we differentiate? Because it's asking maxima. No. Control your mathematics. Take help of
Threshold wavelength.
Threshold wavelength here. So how to calculate threshold wavelength here? Hc by lambda should be equal to work function. Sc value is given. So we have to do that separately. Sc by lambda naught should be equal to work function. Okay, we know Sc. So this lambda naught is what? So I'm going to bring that one. So this will be So this is 2 electron volt. Bring that one here, solve for T, we'll get that particular time that you're going to substitute. Once the wavelength becomes more than that, no longer the photons will be in a position to liberate electrons, and so no further flow of charge will occur. I think that is what the maximum finish over. I think this will be one E will get cancelled, eliminated here, no? So this will be 1,400, 12,400. Here one E is there, that will get eliminated with that. Okay, let me write, this is electron volt, let it be. So this will be, the value of S is EV. So for anybody, these calculations will be difficult. You must manage. This is what very important. I'll call that
Need of
as,
time, sir.
no, the
We only
time.
need value of wavelength, no, sir.
If you want to substitute or directly substitute the T, no?
Likely we can substitute 3000 plus 40T, no, sir.
Anything. So I just wanted the time at which it will stop. Because why I should think about the time? You look at the question. You can't take it for granted, no? The signal switched on and off for time intervals of 2 minutes. For 2 minutes it's on, or for 1 minute it is off. Better to calculate time will be on safer side.
Eighty seconds.
T equal to 80 seconds. Okay, this T I'll substitute. That is the maximum current. Huh? What happened?
12,400 by 2, sir. You did reverse.
Oh, this is yeah. Okay, solve for T, you get 8 cents. That T you substitute for maximum current. For T greater than that, will there be any flow of current? The question is, I think, better to, for T equal to photoelectric effect occurs. For T greater than, again for T, okay, 120 seconds to 80 seconds, no PEF. Okay. Then anyway, like the signal itself will be switched off, no? Okay, just I think to be on safer side, no, I just, we should have this data. It's there in, I think DPP, this answer, you check it later on.